So today we are talking about the other functions, not your linear ones, not your quadratics, not your exponentials. We're talking about all the other functions that can classify under these models. So today we are going to graph them and analyze these different functions that are in the form of ax to the m plus bx to the n, so on and so forth, where m and n are indeed integers. What's the symbol for integers? It is a z. And what you might actually see is this type of notation. So just to be aware, that does mean that m and n are elements of integers. So, like I was saying before, we have your linear functions, okay? Linear functions are when that exponent has a, what number? What number is that if it's a linear function?
2. 1. 2.
Which one, 1 or 2?
1. 2.
If it was a 2, what function do we know are these?
Right.
So it is 1. Yes, linear would be 1. Quadratic would be 2. Exponential, the exponent is actually a what? No, not a fraction, not a sign. Think exponentials. No, probably. We'll make something an exponential function. Say again?
It's a variable.
It's a variable. That's what makes something an
I
exponential.
wasn't sure, so I was kind of
Exponentials, the exponent is a variable, so literally, like, there wouldn't be a number here, or there wouldn't be a variable here, it would be a number, and it would look like that. That's an exponential function, as we did before you guys left for break, okay? We already talked about those 3 types. Now, your other types, such as your cubic functions, is when the largest power of x is to what degree? To what number?
3.
3. Okay, so those are the ones that are in the form of ax to the third plus bx to the second plus cx plus d. That's the general form of a cubic function. What you see here are examples of 2 different types of cubic functions. Do you realize that cubics could also be graphed this way? Okay, so be aware of that. And when you look at either one of these 3 graphs, the pink one I drew or the other 2 that were the way they were copied, what's the domain? Negative infinity to infinity. That's being written in interval notation. Do we put parentheses or do we put brackets around these? Parentheses, because infinity is not included. If I wanted to write it in set notation.
Wait, hold on.
Via x.
Negative x
Isn't that weird?
is less such that.
Yes, such that.
How do you represent negative infinity to infinity?
All
All real numbers. So how do you represent that? All real numbers.
So x and then that e looking thing and then r.
X is the element of all real numbers. So there's 2 different ways that you can write it. Don't be confused if you do end up seeing the element of real numbers up there. Don't be like, what does that mean? Negative infinity to infinity. Okay? These are your basic cubic functions. Okay? A, B, C, and D, they all represent some integer, some number. Okay? It could be real. It could be irrational. Definitely not imaginary, because then that's something completely different. Okay? And the one beauty about these other functions is that you're not going to be asked to write the equation. Okay? Unlike quadratics or exponentials or linear functions, you'll be asked to write those types of equations. But ones like this, cubic functions, they're going to be given to you. Okay? It'll be more of a matter of, given this equation, can you answer these questions? Okay? For example, it says the number of fish F in a pond from period 1995 to 2010 is modeled by this function. You need to make one correction. I misplaced the decimal point. It should be negative 0.030. Please make that change. Negative 0.030. X to the third plus et cetera, where x is the number of years after 1995. Now it says use your graphing display calculator to sketch the function for 0 is less than or equal to x, less than or equal to 18. Okay? Use your calculator. Type this in. And you need to make sure before you click graph that you do what? Fix your window. make sure you fix your window. So go ahead and type in that function, make sure you make the change, okay? And then change your window. What am I fixing my window to?
Zero.
And where am I gonna plug in 0, where am I gonna plug in 18?
Zero. Right there. Where you have X value.
Okay? So then my max would be 18. Okay? Now, depending on whose calculator you're using, what was the window set to before? Like right now, I have a pretty crazy window. All right? I'm just gonna go ahead and change that to the normal -10. Well, actually, no, I'm not gonna change to the normal -10 to 10 window because it probably is gonna be a little bit different than that. Look at this equation. What's my y-intercept? Where's it gonna cross my y-axis?
67.
It's 67. The constant is always the y-intercept. So I need to make sure I can at least see that 67. So what do you think is going to be a good y-min, y-max scale? Bless you.
75. 0 and 500.
Whoa. To 500?
Negative 75 to 75.
Okay. I like 75. I'm a lot smaller. I'm going to go ahead and keep it at 0 because I am talking about a fish in a pond. Can I have negative
Oh, no.
fish? Yeah, so I'm going to keep it at a positive. So now when I graph it, get a pretty good sketch. Doesn't it look like a cubic function? Like a flatter out cubic function? So that's exactly what we're going to sketch. Okay? We're going to sketch that onto our paper.
Oh wait, I know what I see.
And you go
what it is, because it just goes straight up. What do I do? Oh.
Yours do this, so then zero.
What?
I done goofed down there.
Mine looks like that. I just put it in wrong.
You have a really hard time not sketching. So now we have to find the number of fish in the pond after 6 years. Okay, how do we do that? How do we find the number of fish?
Plug 6 into our y, x.
X. Yes, you can look at the table, okay? However, this did happen on your midterm. Somebody showed me the work. Like, they actually showed the plugging in part, okay? And after that, they really didn't show me anything else. But for whatever reason, they got the number wrong. But they didn't lose all 2 points. They at least got one for showing that plugging in part.
That was probably.
And then you can also, and then maybe use the table, okay? But at least this kind of like solidifies you actually getting a method point just in case the number is wrong for whatever reason. So how many fish are in the pond after 6 years?
Oh, that's a little bit.
Well, let's use our table, okay?
Yeah.
Second graph, I need to go where x is equal to 6, okay? And if I look, I have 50.08. Now we're talking about fish here. Can we have a fraction of a fish?
No.
So are we going to round to 50 or are we going to round to 51?
51. 50.
It's going to be, it's actually going to be 50.
What? Why?
Because you're talking about fish, or you're talking about people, or you're talking about bugs, or population, or whatever. You never want to account for the fact we're still missing 0.92 of a fish. So we can't just say, okay, yeah, the 0.92 is there and just round up to 51. We technically only have 50 whole fish. Okay, but when you're talking about time is different. Okay, so like how long does it take for an amount of money to double or something like that? You can't say that'll be 50 years because technically we haven't doubled yet. It's a little bit into that 50th year, so it would be technically 51. So with time, you round up. People or humans or fish or anything like that. Humans are the same, you round down. Okay? Now let's see about 13 years. What about 13 years? How many fish do we have?
56. 50.
Is 56? Good stuff.
Miss Anderson?
Yeah. All right, let's look at the next one. It says a pandemic is modeled using the equation that you see there. Okay, another cubic function where x is the number of weeks after the outbreak started and y is the number of cases reported. So we're going to do the same thing when we use our graphing calculator to sketch the function between 0 and 30. and then we're gonna find the number of cases after 10 weeks, 20 weeks, and then determine if this is a good model or not, okay? Now, I think you guys kind of got this, right? Can we just do this? Let's give it a try, okay? I'll give you a few minutes. Graph it, fix your window, and then look at, figure out how many cases we have, and then determine if it's a good model. Alright, so with this one, what did you set your window, of course your X-min, X-max is 0 and 30, but what about the Y? How does the Y work out?
See, I just
So
put
it's not-
10,000 for my eyes.
Okay, did it look like a cubic? Did it go up at
Yes.
all, make a little bump or whatever?
Yes.
Did it cross the Y-axis?
Yes.
No.
At negative like 5,000.
What?
At negative like
Never
3,000.
crosses the Y.
So it kind of looked like this a little bit, yes?
Yes.
Okay. How many cases were there after 10 weeks?
4,000.
4,000 cases. What about after 20 weeks?
5,000.
5,000. Good. You can always use the table to figure that out, or you can plug in the value. And for X works as well. Now, is this a good model?
No.
If you say yes or no, more than likely you're always going to have to explain why. Okay? So if you said no, why? If you said yes, why? Doesn't matter.
Because it could be either one.
There's only one answer.
Oh.
So I want to know the reason why you say yes or no.
I said no because at X equals 0, you got Y equals like negative 3,000.
Okay? So basically you're saying that at the initial week, the very first week, we're sitting at negative cases, which is truly not possible. Did anybody say no for another reason?
No, because that's not how diseases work. It wouldn't plateau and then shoot up again.
Yes, that's true. Pandemics, okay, they're like, they take over the world, like viruses and things like that, okay? They don't, you're right, they do not level out, okay? They continually increase.
So
Pretty much, and then we just start over.
Pandemics happen.
like the flu. Flu's killing people.
Alright? Questions about cubics? After a cubic comes a quartic. A quartic is when you have a exponent that is 4, okay? And that's broken down as ax to the 4 plus bx to the 3rd plus cx squared plus dx plus e. The domain of a quartic function is negative infinity to infinity, just like a cubic, okay? Now what I want you guys to do right now is I want you to take a moment and I want you to plug in some numbers for A, B, C, D, and E and graph the function. Okay? It could be any numbers. Now let's not be too crazy. Alright? I wouldn't suggest putting anything like 100 or 200 or a million in for any one of these variables because you want to be able to look at your graph without really manipulating your window. Okay? You can use negatives as well. Okay? So go ahead and plug in any numbers. So I want to kind of get some different graphs around. And then I want you to write what you can say about the shape of the graph of a cubic. Okay? Pick any numbers that you want. Did you guys get your graph in? So at some that look like a W, is it a W pointing up or down? Okay, W pointing up. Okay. I heard a quadratic. Is a quadratic pointing up or pointing down?
Pointing down.
Pointing down. So you might have something like this. Okay. Anybody else get anything?
I'm not pointing down.
I already drew it. Here we go. Might as well point it up. Anybody get anything different? A little weirder?
Actually, mine looks like it's doing this. It looks like it's going like this, and then like thinly makes another U, but it's so thin.
Okay. Well, what can we say about the shape of these graphs? No matter what you plug in for these numbers, what can you say? What can you say about the shape of think? What do all four of these have in common?
The max and the min. I'm just kidding.
Either both ends pointing up or both ends are pointing down.
Both ends point up or both ends point down, going towards positive infinity. Both of them are going towards negative infinity. Yep. Okay. So no matter what, both ends are going to be doing the same thing, going up or both going down. Okay. If one went up and one went down, more than likely it probably wouldn't be a quartic. It might be a cubic, or it could be a quintic.
Oh,
That's a good one. Okay. But yes, mostly quartics are going to look more like the W. Okay, depending on the size, the larger the number gets, the more quadratic-like it looks. But basically, there is still like a little mini hump, up there. It's just that it's so tight that you really can't see it unless you zoom. Okay, quartics basically look like W's. All right, so don't be too confused or thrown off. Now, other functions could be ones where your exponent is negative. We haven't looked at those just yet. So I want you to graph this in your calculator. Go x raised to the negative first power. Okay? And before you click graph, go back to a standard window. How do you go back to a standard window? Zoom 6. Okay, so plug this in to your y equals and then hit zoom 6. It takes you back to the regular negative 10 to 10 window.
that's cool.
What does it look like?
Looks like a U in the third column and a U in the second column.
Like a real U?
No. Like a C.
Right underneath?
Yeah.
Yeah. And it doesn't touch the Y or the X axis.
Doesn't touch Y or X. Is there another part to it?
Yeah, on the other side.
These right here, these are known as your rational functions. You would have learned back in Algebra 2 that when you have a negative in the exponent, that's the same thing as saying 1 over x. A pen starting to smear. Try this again. Okay? That's what those look like. It looks like it's not touching x or it's not touching y. What about ones like this, x to the negative 2? Graph that real quick. Standard window. What do those look like?
Eiffel Tower. Yeah.
Volcano.
Like I like that one. Like a volcano, right?
Oh,
Like this a little bit? Okay? That's very different from the one when it was x to the negative 1. Okay? Let's do one more. What is x to the negative third power? What does x to the negative third power look like?
Let's see.
It's a mixture of both of those.
It's a mixture of both of them.
Like a golf club and a.
So one side of the volcano goes down. So kind of like this one.
Yeah. But looking like the other one.
It's curved
You feel me?
Okay, so it has the same pattern as -1, but it's not as spread out as -1, right? It's kind of like a little closer. Okay, but it's more like this shape, right? So you can assume that x to the -4 would look like what?
That shape.
Would look like this one. Yes, all of your odd negative exponents are going to look more like your x to the -1, and all your even ones are going to look like the one that you see over there to your right.
So,
Yes.
all negatives will be opposite regions of each other, negative and positive, and then one's on the y on the x-axis, and then the other.
I think what you're trying to say is that you're going to have opposite. The branches are going to be opposite of each other when it's negative and when it's odd. When it's negative and even, they're going to both be on the same. Like they're both going to be at the top, they're both going to be at the bottom. What would actually cause this to be at the bottom? Like what would cause your graph to look like this?
Negative.
It would be a negative. Okay? So that would be an example of negative x to the -2. Okay? And along with that, These could also be switched like so, and that would be a negative x to the negative 1. Okay? Now, all of these graphs, they don't touch the x-axis, do they?
Nope.
They don't touch the y-axis, do they? So what happens when a curve gets really, really close to them but never crosses or touches? What's that called? It's an asymptote. So these types of functions, when you have a negative integer in the exponent, they have asymptotes. Okay? Of course, they'll have two branches that will get really close to the y-axis but never cross or touch. They do not overlap each other. They have a vertical asymptote, x equals 0. And they also have a horizontal asymptote, y equals 0. Now, do you realize that, yes, they can change. It won't always be x equals 0 or y equals 0. We're talking about your more basic ones, like the ones we just graphed. Different things can cause your vertical or your horizontal asymptote to change. However, you do have your calculator. You can graph. Just take a second after you graph to take a look. What's happening as x gets really large? As x gets really large, is it approaching 0 or is it approaching a different number? Is it flattening out at the x-axis or is it kind of flattening out, kind of looking like it's getting close to another number? Same thing with your vertical asymptote. Okay? Now, yes? So, these are just some basic properties of all these different types of functions. It's more along the lines of like damage control. When you get to these types of functions and you have to graph them and you're like, oh my goodness, this looks kind of weird, looks kind of funky, did I do it right? Okay, you do have to realize that the ones that are raised to your negatives, they are going to look a little bit different. Okay, they're part of a different type of function, rational functions to be exact. Okay, not every rational function will look like the two that we graph. When you look at some of these problems that we're about to do, you'll notice that they're not always going to look like that. Okay, and it's also good so that you guys can have an idea of what a cubit looks like or what a quartic looks like. So that way, when you graph it and it does look weird, you'll know. So we're gonna look at some examples. Okay, let's take a look at the very first one. All right. We have a rectangle. Has an area of 1.5 meters squared. Let the length of the rectangle be y and the width be x. Okay. There's no picture here, but sometimes I think a picture really does help. So let's draw a rectangle. And what are you going to label your length and your width? Let's try to make it all true, but which one's going to be y and which one's going to be x, just for consistency purposes.
Oh,
Top
length.
is y. So I know what that is. So y is.
All right, so we're labeling this x and this y. Now it says to show that y equals 1.5 over x, and as many times as I talk about show, of course half the class is not here, as many times I talk about show, you cannot use a 1.5 over x at any point in time when you're trying to show something, okay? Treat it like you don't even know what y equals, and you have to figure out what y equals, and it needs to be that, okay? So, that means we have to use everything else to determine this. We have to use what's in the given part, what's in the given equation, the given problem. We know that area equals 1.5. What's the area of a rectangle?
Length times width.
Length times width. So we know that area equals length times width. And don't we know the area already?
1.5.
And what's length in the problem?
Y.
And width?
X.
So is there a way that I can solve for y here?
No.
You could
Divide by x. And by dividing by x, I get 1.5 over x equals y. Exactly what they wanted me to show what y equals. Okay? Some of them are as simple as that. Okay, doing a formula, plugging in the numbers. Sometimes you might have to do a little bit more manipulation. But in the end, at no point in time did I use 1.5 divided by x. Does everyone understand that? Okay. Now, it says use your graphic display calculator to draw the graph of y equals 1.5 over x. So go ahead and do that. And I want you to also answer C, D, and E as you do it, okay? So what does this graph look like?
Yeah. X and negative 1.
Look like x to negative 1, but because I was bounded between 0 and 10, it was just like that one part of the branch, right? What happened the closest that x got to 0?
Curved away from
do you mean curved away?
Like it.
Wait, as the closer it got to zero,
It stopped going towards zero. It
Well,
curved up.
it curved up. Going to where? Where do you think?
The closest to zero it can get.
Okay, that's what happened to x as x got closer to zero. But what happened with the graph? The closer that x got, the graph
Went up in the y. The y went up.
to what? To what? It went towards infinity, okay? Y went to infinity. And what happened the closer you got to 10? It got closer to what?
Zero.
Zero. Do you think it ever will get to zero?
No.
So, you have your equations for your vertical and horizontal asymptote. What's the equation for the vertical asymptote?
Y equals 0.
Careful, vertical. So it should be
X equals 0.
x equals 0. And they are equations, so you want to make sure you include the x equals part. And what's the horizontal asymptote? Y equals 0. Please make sure you do not mix your x's and your y's.
Can you explain it?
Asymptotes are imaginary lines that the curve is going to get really close to but never cross or touch. The closer that this curve is going to get to 0, okay? So basically, the smaller that x gets, okay? 1, 0.5, 1/3, 1/4, 1/8. The closer that it gets to 0, the larger the numbers are going to get. Which means that this graph is going to continue to curve up and get really close to the y-axis but never cross or touch.
So why would x and y equal 0?
Because x equals 0 represents your vertical asymptote. The vertical asymptote, again, is a line that the graph is going to get really close to, a vertical one, but never cross or touch.
Oh.
It works the same way with your horizontal asymptote. It is an imaginary line that the graph is going to get really close to, but never touch or cross. In other words, there's no way, the bigger the x gets, no matter what number you plug in for x into this equation, you'll never get a number that's exactly 0. It's going to get closer and closer and closer to that boundary, but it's never going to actually cross it or touch it. Okay? Other questions? A taxi company fares depend on the distance and kilometers traveled. We have this fare right here, how it's calculated. X is the number of kilometers traveled in euros. Sketch the graph. Tell me the cost and the number of kilometers traveled that gives the cheapest fare. Gives me the cheapest